Now I want to introduce David Krisiloff. I learned last night he got a PhD in chemistry from Princeton and still has a reputation in the department for going through the most brutal qualifying exam. So he's gone through that, he can go through this. So, all right, welcome David.
Thank you. This actually fits in really well with Hiram's talk in the sense that it turns out getting large quantities of labeled data is rather hard. Yeah, all right, oh, this is much better now. All right, yeah. So I'm going to be taking a slightly different approach today to the problem. Rather than going to semi-supervised learning, we'll talk about how we actually label data and how that actually changes over time. But it's essentially the same kind of questions about how do I build a sufficiently large data set for these models that are very, very hungry for labels. Okay, so my real focus here is measuring malware with crowdsourcing. There are a whole bunch of interesting machine learning questions that intersect with malware analysis. Things like antivirus, is this good or legitimate versus malware? Functionality or family descriptions. Is this a downloader? Does it come from a known family? Is it a reverse shell, et cetera? These are all things we can tackle with supervised learning, assuming we have a labeled data set. And it turns out if you look in the literature and also what people have been talking about in industry, there are great sources to get labeled data. VirusTotal, VirusShare, reversing labs, these are all things where I can go out and not just get one person's opinion on is this malware or what kind of malware is it, but I can ask a whole lot of experts. And so today I'm going to talk about A, the algorithms we use to build up labels from this crowdsourced data, and then B, some interesting things to note about how these labels change over time and how they may want to affect how you build a data set or how you actually move these things into production. So just so we're all clear, in case you haven't seen VirusTotal or VirusShare or reversing labs before, very basic, simple data. For a particular file, I can see a variety of different vendor responses. So these are all different AV vendors, and they all say different things about this particular file. You'll notice two of them on this very limited subset believe it is malicious. And you'll see different labels. So I'm mostly interested in binary classification. Is it goodware or is it malware? But if you're interested, you could definitely parse a bunch of the AV responses and think about things like, does it belong to a particular family? There are also two vendors here who have said nothing. They believe that the file is in fact goodware. So we're already seeing that experts definitely conflict sometimes about whether or not something is good or bad. And the other thing I want to make note of before we move on is the timestamp. So because I'm interested in time here, we need to figure out a reasonable timestamp to use. So I'm going to be finding sample age here as the last analysis time minus the first submission time. I don't know how old the file actually is. This thing could have been distributed on the net a decade ago. It turns out there are not really great, reliable ways of figuring out how old the sample was. Many files have a compile time in the header. There are both legitimate and malicious reasons why you might want to screw with that. So the easiest thing to use here is just how new or how old the file is on the crowd sharing platform itself. If anyone would like to debate what timestamp they want to use, I'd love to hear alternative opinions. Let me know. Okay, so given a bunch of different expert opinions on whether this file is malware or not, how do I construct a label? I want to build a labeled data set. This is a really interesting area in machine learning. I can't do it justice in one slide. So if you're interested, please check the literature. There's a lot of really cool stuff out there. Labels from Crowds 101. The simplest thing you can do is a majority vote. I have 60 plus vendors. More than 30 claim it's malware. I'm going to call it malware. If less than 30 call it malware, I'm going to call it goodware. It turns out, A, really easy to code. B, it's actually optimal. In this scenario, I believe each AV vendor, each of my crowdsourcers, is equally accurate. The best thing you can do is a simple majority vote. For today's talk, we're going to use two different labeling algorithms. The first comes from the Ember dataset, which was an awesome contribution from Endgame. I'm going to call it a majority vote. It's not actually a majority vote, but in fact, each AV vendor is treated equally like you would in a majority vote. And their basic algorithm is if you have 0 detections, we call you good. If you have more than 40, we call you bad. And everything in between is unknown or unlabeled. So we're being kind of conservative here, and that's probably not a bad idea. We'll talk multiple times in this talk and reiterate the idea that mislabeled data reduces my classification performance. And so it's not a bad idea to be conservative when labeling these data sets. Now, if you believe that, hey, not all vendors are equal, that there are some AV vendors who are a little better than others, then what you don't want is a majority vote. You wanted a weighted average. Those vendors who are more accurate should get a little more say in whether or not I call this file malware. It turns out almost all these methods derive back to a paper in 1979 from Dawood and Skeen. From a purely unsupervised standpoint, I can both estimate the labels and the individual vendor accuracies with an expectation maximization approach. And it turns out, while people publish new papers all the time in this field, most of them derive back to this original statistical model. It's effectively naive Bayes. We treat each vendor independently. And for today's talk, we're going to use one variant published in 2015 from Netflix and a couple other different research universities called Better Malware Ground Truth. And this is effectively a Darwin scheme model where we have Bayesian priors on a couple of my parameters. So before we move on, it's worth asking the question is like, these are great ways of doing crowdsourced data. If I have some data set, I want to go to Amazon Turk and label. These are actually really great ways of handling that. However, I'm interested in antivirus, and antivirus data changes over time. None of these talk about anything about time. So it's worth asking the question, because these are designed for kind of single instance, build a data set. If I'm in production, if I know, hey, AV vendors are going to improve their accuracy over time, their new APT groups, their new pieces of malware, and not everyone knows day one what they are these necessarily the right models? So what we're going to do is we're going to take a bunch of data from these crowdsourcing platforms. We're going to look at how it changes over time. And then we're going to look at how these algorithms deal with that noise. And it turns out they are not super resistant to this kind of noise. All right, so the theme of this slide, AV changes over time, is everyone makes mistakes. All AV vendors in this slide have been anonymized. If you slice and dice the data enough, you will find someone making a silly mistake somewhere. It turns out AV is harder than I would naively think, especially across millions of files on day one. So I have in this graph vendors blue, orange, and green. And this measures how frequently you see them change their mind, either saying it's goodware then switching to malware, or malware switching to goodware as a function of time. And you notice this decays rather rapidly. So you might kind of think, hey, in the first week or first month of seeing a sample, there's some uncertainty about exactly what it is. But this stuff converges fairly fast with time, which is good. You'll also notice there is a distinct tail, even 2 or 3 months out. You see a small percentage chance of seeing an AV vendor flip from goodware to malware. We are not the first people to have noticed this. Everyone in the field has noticed this. Any paper you read on, say, Android malware classification, Windows malware classification, who uses data from these platforms said something like, and we waited 6 months, or we waited a year before using the data to make sure it wasn't changing anymore. And in fact, you can notice this in the streams of data simply by asking how often do I see certain sample ages. There are a whole lot, there's a spike here at day 1. There are a lot of new samples coming in. There's also a really big spike at day 28, which to me smells a lot like somebody knows things change in the first month a lot, so we're just gonna rescan everybody after the first month and see what my competitors think. So I think everyone in the field who's been doing this enough knows that this stuff changes over time. There was a particularly curious paper out in 2013. It got a little cut off from the slide, I'm sorry. That was interested in measuring software regressions on these platforms. And so what I naively thought as a data scientist who did not have any subject matter expertise is that AVs all work like the top one here, AV vendor 1 in blue. I call a file good. At some point, I realize it's malware. I produce a signature. I add it to my engine. And from that point forward, it is always malware. That is how I naively thought it worked. Interestingly, there are a bunch of vendors up here that does not seem to be the case. If you look at vendors 3, vendors 4, 8, and 9, I think I got them all. At some point after realizing the thing is malware, they go back and call it goodware. And in fact, a couple of these change rather rapidly over a course of single days or weeks. So there is a fair amount of noise in this data. This is not the most common thing you'll see, but every vendor seems to make occasionally these mistakes. Now you can ask yourself, if I'm building a labeled data set, what happens if I accidentally pulled data from the service on the wrong day where some of these gave me the wrong answer? Everybody has a little bit of noise. How tolerant is my aggregation algorithm to this noise? So this is single AV vendors. Let's talk, I apply one of these labeling algorithms to this data. Do I see changes over time? So I'm going to be making a number of plots that look like this. So let's walk through it slowly. It's an interesting plot, but it takes a minute or two to digest. We have data collected from 2017 and then rescanned in 2018, 6 months later. So this was October 2017, March 2018. On the x-axis for each of these files, and these are all Windows files, so that's what we're primarily interested in at the moment, we have the total number of detections on these platforms. That is how many vendors believe the file is malware. On the y-axis, the same thing in 2018. So to situate yourself, the y equals x line is there is no change over time. Whatever I thought in 2017 is identical to 2018. The further away from that line you get, the more change we see over time. I've attempted to encode a little bit of density information with some transparency. It doesn't come through very well. The very edges of the distribution, which are a little fainter, are less common. Really, really large changes are not that frequent. All right, so we're going to take this graph, and I'm going to color it by different labeling algorithms, and we can see how these labels change. So on the left is Ember. Remember, this is the majority vote. We treat everybody equally. On right is the better malware ground truth model, which again is a weighted average. Red things are malware, blue things are goodware, and yellow is my unknown or unlabeled category. Let's start with the Ember because they're a little bit easier to see. So this is all my goodware in 2018. You'll notice, interestingly, Ember, remember, 0 detections means goodware. There are a bunch of files in 2018 I would label as good that had I built the data set in 2017, I would not have labeled. So you'll notice we go up to almost 10 hits. So there is some change over time there. There's this peculiar island or peninsula up in the north of the graph. These are files where back in 2017, 20-ish vendors thought it was bad, and now 50 plus think it's bad in 2018. The simple explanation is some people on VirusTotal knew what was going on ahead of time, or VirusTotal, reversing labs, et cetera. They knew what was going on ahead of time, but the community has actually caught up in the last 6 months. But again, my labeling algorithm said I needed 40 plus hits, so even though this is, we think now in 2018 malware, we would not have labeled it in my data set in 2017. The better malware ground truth picture is a lot less clean. There is some unknown stuff in there. It's hard to see. Take my word for it, but there's not a lot of it. The big difference ends up being that this labeling algorithm is far more aggressive in labeling samples. There's a lot less unlabeled stuff. Notably, I'm not going to tell you that that's a good thing or a bad thing. Depending on what you're doing, this is either going to help or hurt. However, it doesn't really answer the question how much change there is over time. Hopefully you can see at least in portions of the graph we're seeing change. So we're going to recolor these pictures one more time. I'm going to color everything gray if there was not a label change, regardless of what label it has, and orange if there was a label change. All right, so you can quickly see Ember has these nice quadrants. These are things that were malware that became unknown, or things that were unknown that became malware. There are similar quadrants again for the goodware. The better malware ground truth is a little more complicated and has some really interesting dynamics going on. In addition to your unlabeled to labeled, there's also some goodware to malware changes as well. So hopefully at this point, you'll at least agree with me that time is an issue, even though I'm aggregating many, many different vendors, and each vendor by themselves does not make a whole lot of mistakes. These label algorithms do produce different things over time. So to level set, mislabeled things reduce my classification performance. There are some interesting papers out there for deep learning that if you apply label noise in precisely the right way, you can regularize your network. That's not what we're doing here. Mislabeled things are going to reduce my performance. If I knew which of these were mislabeled, we could do a bunch of things. We could remove them from the data set to begin with. We could probably schedule them to rescan them later on to get better labels. We could include them potentially in a semi-supervised learning case as the unsupervised examples. So this, I think, fits in rather well with Hiram's work. There's a difficulty in getting these labels and making sure they're right. So the question I'd like to ask today is, can we predict how our crowdsourced labels are going to change over time? Because if I can tell myself, like, I have some malware now, but I don't think it's going to remain malware in 6 months, I might be able to improve my model by not including it when I train. So modeling label changes ends up being both easier and harder than you'd think. So to be explicitly clear, graph on the right, what I want is a classifier. Given antivirus vendor output, I would like to know, is my point going to be gray or is it going to be orange? That is, do I think the label is going to change and then I'm going to route it and do something else with it? Again, this is from FireEye's 2017 ingest. There are 250,000 files. We rescanned them in 2018. To level set here, this should work. The vast majority of files don't show a tremendous amount of change over time. It's certainly not the case that AV vendor responses are independent with time. They should correlate. I don't go to VirusTotal or reversing labs and see brand new information every day when I scan the same file over and over again. But there's no way this should be perfect. If I got 100% accuracy with this algorithm, I could tell you, here's today's label, but I know it's not tomorrow's label, or it definitely is tomorrow's label. And you could work out a really, really good AV engine without ever seeing the file. That, to me, does not pass the sniff test. It seems unlikely you should be able to do antivirus without actually seeing the file. And so if I see any, or present anything to you guys today which has 100% accuracy, know that there was like some sort of data leak in what I did, and I screwed up. The model shouldn't be doing that. Basic inputs here are going to be my AV responses. The current label of my labeling algorithm, the sample age, which turns out to be rather important, the number of responses from different AV engines, the number of different detections from the engines, and then each of the individual vendors encoded with a 1, 0, or -1 on the cases where they didn't respond. Now, we're cheating a little bit. It turns out a number of these platforms also provide a little bit of metadata about the file. something about what kind of file it is. Does it hit any known magic bytes so we know this file's packed or it's been somehow encrypted? And we can include that as well into the model. Overall, there are 250,000 observations and 135 features. So we threw this at 2 different gradient boosted tree models, one predicting Ember labels, one predicting the better malware ground truth labels. Again, class here, no change means the label has not changed. Change means there was a label change, regardless of what it changed to. Change here is a minority class. I did not set up the data sets well for this particular problem. The class imbalance is roughly 1 to 10. That is, for every 10 samples that there is no change, there is only 1 that there is. It's worse for the better malware ground truth than Ember, but again, this had a lot to do with how I built the data set. The recall for the minority class isn't bad, 0.85 for Ember, 0.86 for better malware ground truth. And you can see the confusion matrices on the right. The largest errors we're making are going to be false positives where we believe there's going to be a label change and there in fact is not. The most important features here, it turns out sample age is really important. Things that are newer are more uncertain. We kind of knew that already. The total number of detections is important. The total number of vendors is actually important for reasons I have not yet quite figured out. And then a couple of individual AV vendor responses. So we are pulling out some correlations between different AV vendors to try and understand if these are going to change. Well, that's good. I'm under time. All right, let's skip to a backup slide really quick because I got time. All right, everyone makes mistakes, part 2. How did I make mistakes here? It turns out this particular model, while generally doing pretty well, has some categories where it makes a whole lot of mistakes. So if you take a look at this, what we're saying is let's break down label change or not label change to what kind of changes are occurring. What you'll notice is that for certain quantities, we're doing really well, and certain types of label changes, we do really badly. So goodware staying, goodware no label change, we do good. Malware staying, malware is good. Anything we didn't label it to begin with, but changes, we do pretty well. Malware changing to unknown or goodware changing to unknown, we do really, really badly on. Our accuracies are 22% and 41%. Notably, those are the ones that we have the least support for. That is, there's simply less examples of really large changes in our data set. This tends to be true regardless of labeling algorithm. This stuff was Ember. You see it in better malware ground truth. We've done this for the internal FireEye labeling algorithm, and you see the same thing. Really large changes are hard to predict. You could argue this is a data set problem. I need to collect more samples like this. However, at least as a human staring at reports on AV vendors for these compared to the ones that did not change, there doesn't appear to be anything in the report that indicates there should be a change. You can imagine, certainly if I called it goodware and now it's changed to unknown or malware because it was an APT thing and it was exploiting a zeroed I no one had seen before, there is literally no information from AV vendors 6 months ago that explains what's going on here. Nobody knew about it, and there's no reason our machine learning algorithms should be able to understand what's happening. So again, reasonable results, anything close to 100% is really funky. We definitely aren't getting there. All right, so conclusions. Crowdsourcing is a super convenient way of building up my large data set. These models really, really want a lot of labeled data, but using these types of antivirus data has non-trivial temporal effects. You should be aware of the fact that your labels are going to change out from underneath you. Our best approach for trying to handle it at the moment is trying to predict these changes before they happen, either to rescan them later on, to remove them from our data set, or apply some other approach. Notably, we have a couple of interesting ideas for things in the future to go beyond this. First being, we're using these models that don't include time. We should just go off and include time, which turns out to be much harder than I'm making it out to be. If anybody in the room is an expert on exploitation maximization algorithms, come talk to me later. I have a lot of questions and problems. We are exploring including time as a variable in those algorithms. There's another thought that I think is kind of really interesting and very far out there, coming from, at least from my CNET in Caltech, in Chris Ray's group, which is that these crowdsourcing algorithms are always going to produce some sort of uncertainty in my labels. And there really isn't going to be a way of getting around that. And so rather than producing hard labels for my labeling algorithm, we should produce soft ones, that is beliefs on things. Rather than calling it goodware, I'll call it 70% goodware, 30% malware. And for a number, but not all machine learning algorithms, it's possible to adjust the loss function to take that into account. Ergo, getting something wrong, which I think is 60% malware, is less important than getting something wrong where I know it's 99% malware. And that might be a way forward of just living with the fact that there's uncertainty in this field, and there certainly is. All right, so to wrap up, I wanted to thank the FireEye data science team and our malware reverse engineers. I've learned a lot working with you guys for just a couple of months. And I want to thank all of you guys for listening to this talk. If you use VirusTotal, Reversing Labs, VirusShare, just be aware of the fact that the data can change over time. Pay attention to how new this sample is, and go from there. Thanks. Thank you.
Hey, excellent talk. I wonder, did you at all look at the sensitivity based on certain families, like certain heuristic families, or they're big families that are sort of catch-alls, and whether or not those change more in your predictive model?
No, that's a good question. So when I built the data set, one of the things we like to do is to try and stratify to avoid including, say, thousands of a simple family of malware that just has many, many, many different iterations. So, and we can go into more if you're interested, but the sampling algorithms to build the data set should have hopefully taken some of that into account, and that there were many different examples for many different pieces of malware family. That kind of gets what you're asking.
So I understand your premise saying that at any given time that you poll to the majority vote, not the way, do you make different labels? But intuitively, if I'm someone who's using a label, I'm going to pull the latest label, right? Latest decisions from all these things and say I do a majority vote. If I do that, if that's the last update, do you see that's a false assumption, or is it something that?
Yes and no. So there's a subtlety to this that I did not understand until I started looking at the data and then realized I was making a really horrible assumption, which is that the latest data that you can pull from these sites is not today's data. If you can go off and rescan it, you get today's data. But it's not difficult to find cases, at least in our ingest pipeline, where our latest report was from last year, and the sample was only 7 days old then. But no one has rescanned it since. So yes, it is the latest data from that platform, but I know there's a lot of uncertainty associated with it. So I didn't want to get into it too much because it's platform specific, but yeah, the simplest and engineering solution to this is just rescan everybody that I'm going to use today. It turns out these platforms tend to be rate limited, and I simply can't do that. One of the things we are exploring is using this type of model to figure out which ones to rescan given our rate limit capabilities. But yeah, if I could just scan everybody on all the brand new antivirus engines right now, I'd get rid of a lot of this uncertainty.
Oh, I finished that. Okay. Yeah, I was wondering your model for whether or not it would flip. If you thought about switching from a binary, does it change or not, to more of a continuous measure of the change in number of vendors that say it's good versus not?
Yeah, I have a backup slide if you want to see it later on just that problem. It's doable. It highlights one of the things I said before, which is that really large changes are really bad. The basic regression works really well, except for the points on the very edge of the graph where I see like 30 or 40 different vendors who now go, it's bad or it's not bad. The really large changes, the model is unable to learn. But it is possible to learn a model just for that, how many total vendors are going to in the future say this is malware.
Because you had said that one of the highest, like one of the very explanatory features. I would have thought, if I understood correctly, the way you're aggregating over vendors is sort of these arbitrary thresholds of like 40, right? More than 40. So I would think that the prediction is largely based on did it happen to be a
Yeah, definitely. So most of these don't change tremendously over time. So if I know, for instance, you've been on one of these platforms for a year and 45 vendors think you're malware, it is a really good prediction to just say 45 vendors. It's going to be tomorrow's 45 vendors too. I'll show you the backup slide. If anyone else is interested, please stop by. You can have a null model of just predict whatever the 2017 values were for the 2018 model. That does reasonably well. You do better with an actual machine learning model. But there is a non-trivial threshold here where parts of this can be solved with non-machine learning things. I'm a data scientist. Machine learning is my hammer. Ergo, everything's a nail. But there actually is a performance increase you get beyond simple rules here. But it's a good point that most things don't change, and using that initial data is why the model does so well.
Hi, quick question. So I wonder if we can predict large changes if we knew something about the dependencies between vendors, because I don't know, but I find it hard to believe that all 60 of them are doing some intellectual stuff to independently detect malware. So I wonder, and if any such data is available for us to figure out.
So definitely yes. There is a whole subset of these models. Remember, I said the ones I'm using are all based on naive Bayes. Everybody's independent. People have done a whole lot of work in the crowdsourcing field on looking for correlations between crowdsourcers and including those in the model. There's some really cool work. I can show you some of the papers. You can Google and find some of them. It's definitely a way forward of improving the model here. That is an assumption which is totally wrong.
Thanks, David. Nice talk. I have a question. Did you see, or do you have plan to experiment on like the clusters of malware that changes label and the ones that don't change label? Like, yeah, that was my question. Like, thanks.
Maybe it's not a bad idea. I hadn't thought about it. My personal feeling ends up being the ones that have tremendous change end up being things I simply can't predict from the just AV vendor stuff, including actual file features. So pulling stuff from, say, Hiram's talk or pulling stuff from Scott's talk, like actually having features from the file itself as opposed to just what AV vendors say would probably prove accuracy. I would not be surprised if there were certain features of the file that were dead giveaways of something weird might be happening here. But for our current use case where I'm attempting not to look at the file to do this, not yet, but it's not a bad idea. I saw one question from Keegan. Oh.
Just really quick, if we're releasing, say, a public data set of labels, for example, is the information in the report itself sufficient for actually running your model, or did you need to add anything to it?
No, everything that the model learned was from publicly available data from these platforms. Now, granted, collecting large amounts is difficult. Paying them for additional access so you can download the data faster is good. But no, you could have produced the entire data set I have by just listening to these different feeds.
David, I really like the visualization of the vendors sort of switching their opinions, and especially rapidly. Is there a way to build that sort of reputationally into the Netflix algorithm you said, where we implicitly don't trust the finicky voters?
So potentially. So if particular AV vendors are really finicky, yes, because you learn the accuracy of the vendors, and some of them end up being less accurate than others. So you do learn some of that. Now, doing that over time is trickier. We're working on it. I don't think what I have currently works all that well, but it's something we're interested in. We can talk more about it if you're interested. So yeah, sort of.
Any more questions? All right, let's thank David again then.